Oh, and AJ, we'll watch the chat for questions that might come up, and we'll make sure you know about it. Do you want to have questions at the end or as you go through the session?
I have a lot of slides to cover, so let's do the questions in the end.
Okay, sounds good.
As time permits, because I've got a lot of content. I'll tell you this. This one of my most favorite topics. So I'm going to speak in length, and sometimes I'm going to go fast.
Very good.
Depending upon time. So please stop me when I go too fast for people. And because I'll tell you, I believe the content is like vast. Sometimes I can go fast and finish it off in 40 minutes. Let's see that.
Sound good? Let's do it.
So whenever we talk about data warehouses, right? Whenever people hear about data warehouses, the first thing when in 1998, when I started my career, there was no concept of big data. Big data everything came in around 2002 timeframe. I was in a different country, and I was in the retail market. I was working for the retail guys, and then it always throws me out saying that what is big data, right? When you think about data, we all know data, transactional systems. If you have been in the industry for a long time, you will know that you have been working with transactional data, ODS data, and they used to call us a master data and transactional data. There was no big data at that point of time. The concept of big data came in. It is a eureka moment for many of us when we saw Walmart stacking paper towels next to the toilet paper. It is like it used to be. If you know that the paper towels used to be in the kitchen aisle, it was never in the toilet paper aisle. And the reason for that was people who go to the kitchen, paper towels are used mostly in the kitchen to wipe the islands off, if you know what it means. And they started keeping it together. Then they saw a uptake of selling of paper towels even become higher because every time people bought toilet paper, they bought paper towels together. At that point of time, Walmart realized they have a lot of data. They were able to, the reason why it all happened was they had a lot of data. They had like billions of data points to point to them saying that people will buy toilet papers or people who buy paper towels. And every time somebody buys a toilet paper, they want to buy a paper towel, they had to walk across the entire Walmart. So the people would lose focus, get distracted, stop shopping for paper towels and go back home. So when they start keeping it together, they had a 30% uptake of the products. So this all happened because they get millions of transactions every second now. This is a million of customer transactions every hour. It used to be, but now they get like a millions of transactions every minute. So they have 2.5 petabytes of data. These data, the petabytes of data, it helped them to do analysis. Initially, it used to be a visual based analytics. Now it becomes machine learning based analytics. And the reason, if you look at why big data is essential, this is what Walmart says. I'm not saying these things. Walmart said it is an essential part of the strategy of many companies. They do analyze it for various reasons. The top 5 reasons they talk about is making efficient, improving checkouts. You know what they do. But this is Walmart. Walmart retail has been there for a long time. But I want to bring in one more customer scenario, one more scenario, which is very close to my heart now. It's called connected car. Connected cars are like Tesla does it now. If you look at it, they're no longer a car companies. People used to be in Detroit focused. We all know that where Ford and Chevys and GMs are made. But now the cars are being made in California. Tesla, if you look at it, is Tesla really a car company? No, it's not. If you look at it, Tesla gets valued. If a stock market says Tesla be valued like a tech company, Tesla be valued like an Amazon, Tesla will be valued like an Apple, even though they are not producing phones, they're not producing apps, they're producing cars, they're manufacturing cars. But when you value a company, you're valuing based upon the data they contain. They contain how you drive, they contain they're collecting how you drive, they're collecting how you brake, they're collecting when do you start in the mornings and what in fact they exactly know which restaurant you go often based upon the geolocation of the car. So what I'm trying to say is, right, So the big data is around you everywhere now. As we grow in the industry, there is a lot of data, and this data adds up to there are 10 different data points that we need to talk about of data itself. The 10 V's of big data. It used to be 4 V's of big data. You would have heard it multiple varieties of versions of this. I would say is like the 10 V's of big data is it talks about volume, the amount of data, the velocity at which it gets generated, the different kinds of data it provides. Like you can talk about the XMLs, JSONs, and CSV, parakeet formats, and a lot of varieties of data. And then you have veracity of data. It's a source of truth. Where does the data come from? And you also talk about what is the value and vagueness of data, and what is the vocabulary of data. That's a glossary terms of business. And where does the data come from? It adds value into the data itself. And also talks about variability. It talks about how is the data being being invoked over a period of time. And also, it last but not the least is the validity of data. So if you go into if you go into if you talk about any kind of data, you're talking about what is the whether this data is actually good data or bad data. Is it cleansed, not cleansed? Is it accurate, not accurate? All those things forms the big data, the tenets of big data itself. If you don't ask these questions, I would recommend you to ask these questions because this will invoke what I call as a data engineering methodology. It will invoke what I call as an architecture, and we are to talk in length about what are the different things. How does industry grow, technology grows along with what we uncover from the data itself. So people say, oh, technology improved, that's why you are seeing this. No, these have been there for like even before technology came. Your mom and pop shops next to you, which were in 1980s, have the same kind of data, but they've never had a technology that can fuel it, funnel it, to make it easy for them to understand the analytics space. So these are not the important things. I'm just setting up the pitch here. So if you have any questions, please hold off your questions. We'll cover them as we go technical about it in a couple of slides. And when you talk about 10 methods of big data, we talk about what does it mean by in data engineering methodology. How do we do this? What are the different roles and who are the people? I'm going to talk about only 4 things we talk about. One is how do we capture the data? That's very important. How do we capture it? What are the different varieties of capturing it? That data can come in multiple formats, structured, unstructured, semi-structured data. And how do we discover the data? When you discover the data, you are discovering it from multiple sources. You have multiple products that can do automated discovery of data itself. They can go into, if you put the agent in your system, the agent can scan through and say like, hey, there are so many varieties of data that you can potentially capture. And once you capture and prepare it, you have to do curation process. This is the most important is for the business is capture and consumption. But from the importance of to make this data really be useful, become information, become structured, is the curation and enrichment process. We talk about without a domain expert, without a data engineer, without an ML developer or ML engineer, you cannot even curate it. You do not know what it means. So you need to have these roles to help you capture the data, curate the data, enrich the data. You have to add and making sure that you're making it context awareness, bringing context awareness to your data, making sure the data, if how do you connect weather with the number of donuts you sell? So if you look at it, if it's in a winter season, the amount of donuts being bought is low, and in summer season, the amount of donuts being sold is high. So Krispy Kreme, if you want to go and evaluate it, you should go and evaluate based upon data. They will say how weather conditions makes a huge difference for the donut sales. Similarly with coffees, people are addicted to coffee like me. Especially in summer, we drink less coffee because we want to have a hot coffees less and cold coffees go more. And this is simple off the cuff logic saying that in summer we drink iced coffees because it's cold, it's hot outside. We want something cold, and we are coffee addicts, so we go back and buy a iced coffee. So Starbucks keeps iced coffee a lot more in summer than in winter. So these are all like some of them over a period of time. But if you look at it, do they sell iced coffee in winters? And who will buy iced coffee in winters? And what kind of persona it is? How much of coffee should I keep? All those can happen only if you do the curation and enrichment without adding the real data outside external data from external factors. You cannot be even enriching your own data. So that will provide you how do we consume it and how do we make our business add values. So if you look at stock market going bonkers in the last few years, hey, COVID happened, stock market went crazy high. There's a lot of data to say that stock market will go high because people are going to be still be eating food, they still be watching TV, they still will be having relaxed life, even though they are still stuck at home. So things little bit changed, but overall the data fueled the economy itself. But this is all great. This is all from engineering methodology, process, and everything. But how do we do the plumbing work? There is like literally what is the plumbing work? So I just recently joined Informatica 4 months, 4 weeks back. I quit my job in Accenture. I used to be a senior manager in Accenture, and I quit my job and joined Informatica because it's one of the data companies. And I borrowed this slide from them. One of the things that we talk about in with data is it's data comes in multiple varieties. It can be structured, unstructured, and semi-structured. Excuse me. It, it what is an organization own is their data. They don't want anything beyond that. Everything else you can procure it from anybody. You can procure the technology behind it, the methodology behind it from companies like Microsoft, Google, AWS, and they all supply the data with they all supply their environments for the data what the customer brings in. So from a ingestion process, you can ingest any data, any speed, any kind of scalable or incremental or initial loads or high performance connectivity. Everything through happens to data ingestion process. You will be able to first take the data what is available in terms of the varieties and where they are located, how are they being streamed, whether it's coming from an IoT device sitting in a car on the middle of a Route 66, or whether the data is coming from an on-prem environment which is sitting in a data center owned by Verizon somewhere, or it could be a SaaS application like Salesforce or your ServiceNow. So it's sending the data into your analytics space. You collect all this data. And how do you collect it? And then what you do after collecting it is you take it into a curation, and once you capture the data, you curate the data and start enriching the data. You'll be able to take it into a landing zone and then cleanse the data, add value to the data, make it the discovery process happens as how do we how as a technology comes into helps the data itself is through bringing it through AI powered tools to make sure that you are able to transform automatically, not anymore with saying, oh, is this a gender or is this something? Yeah, there's one and zeros, whether it's a male, female. Now we have a lot of more values coming up. So we need to add all those quality and integration that happens, and be it whether it be a streaming data or be it a batch data or be it coming from a different source. Once you do your curation process, you'll be able to set it to a prep and store environment where you can do the prepping, and once you prep and store the data, you're able to model the data. You're able to model for analytics purposes. You can do it in your cloud data warehouse. Some of the things that we'll be talking about in the next couple of slides, more about the different warehouses, what each CSP provides, and they have their own environments in terms of machine learning, and how do they provision the data to perform this analytics space to provide either real-time analytics or enterprise level analytics, or you can do service-based analytics, self-service analytics. All these are able to provide. I'm going to add a little bit of technology here saying you can do stream analytics, or you can do Power BI, or you can do Excel sheets, however you want it, depending upon who the user is. You don't want to go to an executive and give them an Excel sheet saying, hey, here's the Excel sheet full of rows and columns of data, and they don't understand a bit about it because they do not have the patience to go through the data. Whereas if you give them a Power BI, they're going to appreciate it more because they know what the data is. So it's about giving a look and feel for different audience, what the data, how the data has come across over a period of time. So I'm going to switch gears here and then go talk about the different architectures. Now we saw about the methodology, the process. Now I'm going to slow down a bit about different architectures, how each data comes in. We'll talk about when we talk about big data reference architectures. This is one of my favorite slides. It talks about what are the different environment or services each cloud service provider, the three major cloud service providers, AWS, Azure, and GCP, provides for customers. So I'll be mixing a lot of AWS, Azure, and GCP from now on, just to keep it, just to highlight the each benefit, what are the architectures, what each cloud service provider provides. So, but from a reference architecture point of view, if you look at it, depending upon how the structure of the data is, what kind of a variety of data we get, whether structured, semi-structured, or unstructured, streaming data, batch data, or is it coming from you have to do like a real-time ingestion and stream analytics. All those you can be able to do with the ingest process, and you have services that provides like data pipelines, Lambda functions, Kinesis, which is for real-time analytics, and you'll be able to take them through a landing zone, which the landing zone for an AWS, what we call as RDS, which are like a RDS is similar to a transactional data store, operational data stores. And then, or you can do it in a NoSQL database like DynamoDB, or you can do it in S3 buckets where you can store your CSV files as a batch mode, so a file system layer. Or you can do it in an archive straight away from your source system on-prem. You can push it in an archive like Glacier. But efficiently, what you do after you get your data into a landing zone, what you do is how do you use multiple services to cleanse the data or prep the data, curate the data, what are the term I use, but all of them marks to one thing. How are we going to take the data and add contextual awareness to the data itself? When you add a contextual awareness in AWS, what you do is you use Glue. Glue is like Glue in AWS is similar to a data factory in Azure, and it's similar to cloud data flow in GCP. And similarly, we have many more of these comparisons. But you send it to Glue, you do a ETL layers, or you do it to send it to Kinesis Analytics for streaming analytics of data, or you can do EMR, Elastic MapReduce, which is based upon the Hadoop concepts, open source concepts, or SageMaker, which is based on AI concepts. You take all of these different tools to prep and train. And once you're able to prep and train the data, add more contextual awareness to the data, and you can start putting ingesting this data into a long-term storage or analytical storage, what I call it. You can do the models for modeling serving purposes. So you can model the data based upon a data warehouse like Redshift, which will be focused on the next few slides. We'll be focusing on Redshift. And we can also do a data charts, and then we'll be able to send it to a visualization medium like QuickSight or Tableau or Power BI, whatever the tool the customer chooses. They can't go wrong with any of those tools. They're all very popular, good UI layer tools, but these tools provide the value addition to the visualization portion of it. And then you can do governance on top of it, and then you can orchestrate it using, like, for example, step functions, logic apps. You can do monitoring, you can do all these capabilities that CSV provides. But from a big data reference architecture point of view, we are talking about data coming into from the source systems to a landing zone to do the capture and curate after the capture process, to curate and enrich the data, and to add contextual awareness, and to store the data in a big analytical storage that can be visualized, that can be provisioned for visualization purposes. Similar to AWS, Azure has their own architecture. Azure provides a equivalent services. There they are almost very similar in architecture, but they have their own nuances. They have their own offerings curated for customers. So when AWS is focused on heavily on developers, Azure focus on enterprise, GCP focus on innovators. So I'm not going to categorize them like this, but they appear to be focused on all these three varieties of customers. So from an Azure perspective, Azure provides some of the easy to use mechanisms like data factory, Azure functions, event hubs, very similar in nature of structured, unstructured, batch, streaming data. And how do you consume the streaming data and send it to a landing zone, and then where you start your curation process for landing zone. Landing zone is like a temporary area where you store the data before you can curate it, so that you know whether the data that's coming into your environment is actually a good data. Is it actually worthy to be cleansed or should be thrown away? Sometimes what happens is, if you have ever been into a hospital environment, hospitals, before you get admitted, you can get a lab work done. So lab work sends your personal identifier information from the lab before it starts coming in from the admission system. So admission system holds a higher degree of degree of truth when it considers that it's coming from a lab environment. So depending upon where the data comes from, you have the source of truth, and you start making sure that the data what you get is actually valid, is making sure that data is curated properly, is that they're making sure that their source of truth is exactly the source of truth what it claims to be, so that all of them leads to a kind of analytic space. When you before you send it to analytics, before you send your report, you don't want your managing director to come back and say like, is this data valid? That will provide you a complex scenario of saying, how do I provide the lineage of data? How do I able to track the data that says this is the source of truth, this data is accurate? What would have happened if somebody said, oh, you had to keep a can of dog food next to a paper towel in Walmart? It will be making no sense to most of the people, because you by our rational sense of thought saying that all people who buy toilet papers do not buy canned dog food. There's going to be a correlation between them. That correlation, if you have to provide it, can provide only based upon the data lineage what you get it from. So you need to have the source of truth that talks about the data itself. So once you're in the landing zone, once you create the data, you use various tools and mechanisms to curate it. Whether you use Databricks or whether you use Informatica CDI, or you use native data explorers or native HD Insights or Azure MLs, you can pick and choose different tools to prep and train in Azure. And similarly, you can talk about cataloging the data, and you can model and serve the data in a analytics space. The analytics of choice in Azure is Synapse. Synapse Analytics provides everything combined together in terms of pipeline. They have what Microsoft did. It's very interesting. In the analytics space, if you take Synapse, Synapse provides tied up to to the hierarchical ADLS. It is also tied up to the pipelines, and you can model the data within Synapse, and you can store the data within Synapse. So it will look like a self-contained environment of bringing the best of breed, different components from ingestion process to model and serving process within Synapse itself. So all these things, what I said, is of elements of choice. You can choose anything and everything, or you can choose everything to be within Synapse to do the same process, and you cannot go wrong. And Synapse provides multiple varieties. It provides Spark SQL, it provides Spark pools, it provides Data Explorer pools, and it provides SQL pools too. SQL pools, then we can talk about dedicated serverless. We'll cover all those things in the coming slides. But these are some of the things that Synapse provides. And along with it, you can visualize the data in a Power BI reports. You can use anything, Tableau, QA, anything like in terms of Click or Tableau or Power BI. But if you're an Azure customer, if you're using Azure as a preferred cloud of choice, you will eventually use Power BI, because there are a lot of adoption in terms of that Microsoft Azure customers use Power BI. It's Again, there's a big data to talk about it. Am I going too fast? Am I on the right speed for you guys?
Good for me.
Thank you.
No, you're exactly on target, AJ.
Hey, thanks a lot, Tim. So we saw about AWS architecture, reference architecture. Talk about Microsoft Azure architecture. But the next one is the GCP kind of an architecture. What I like about GCP is the different components coming together. I did a big. We took a 50 million of patients data. 50 million. When you say 50 million patient data, combination of with their laboratories, their medical data coming from labs, radiology departments, and order system and billing system, claims, and everything. It was around 8 terabytes of data. We did a POC across all 3 clouds in my previous job. And when I did that, we used GCP to do the work. And when we say GCP, the way the GCP works is significantly different from what I found that Azure and Redshift, the way they behave. I will talk about what the difference in between these data warehouses. But for now, the way the data what we did was we took the source system data. They were all in batch files. We were able to ingest the data using a data flow component. So data flow provides a kind of a integration layer where you're able to move the data. It provides a kind of a data movement service, and it moved the data from point A to a landing zone where we store it in the cloud storage area. Cloud storage is like your blob storage, which is the equivalent of S3 buckets in AWS. And cloud storage contained all the data. We also used Bigtable. For Bigtable is a NoSQL kind of a database. And we also used data lab, and we used data lab to create our models, and we were able to store the data in a BigQuery database, a BigQuery data warehouse. So when we did all these things, we realized from an architecture point of view, there's no big difference. But it all came to underlying saying, how does it scale when you have 8 terabytes of data? So Redshift made as a capacity model that we have to sign up before we know it. Azure provided a flexi capacity model, a hybrid model where it provides automatic scalability and a fixed scalability, whereas BigQuery gave us a complete scalability without even having to say how much of scaling that we need to go for. So depending upon how much of predictability your customer wants, and especially with the data is small, you don't care about the predictability. But if you have a small data, you're going to be tied up with customer wanting to know how much they're going to spend. So depending upon what kind of negotiation the customer has with the cloud vendors, we can choose a different based upon the cloud architecture itself. So this is a reference architecture for GCP that we did. And what did we do is we created all those models of data in from BigQuery. And what we did is we showed the data in. The funny thing is we did the reporting on Tableau, Power BI, both of them, because we had licensing for that. And we showed that the data can be modeled and visualized in multiple ways from any kind of sources. So that was a great revelation for us, that the whole architectures are flexible enough to pick the best of breed of choices, except for that at the cloud level, you have to pick a cloud and then stick to the cloud for each service. But once you are able to get the data, once you capture the data and curate the data, the consumption can happen from either from a visualization layer, or it can happen from a system to system integration. So they're able to tie up with, we tied up with the Synapse with the Dynamics 365 backend environment. So we are able to show some of the analytics in a Dynamics 365 environment too. So there are multiple things that we are able to do in this kind of architectures. We saw these 3 different data warehouses. So what's the big difference between these 3? If I say, hey, everything is one and the same, then why are we having this session? Yeah, there are a lot of things that we talk about as one and the same. If you talk about data backup and recovery, which is the most crucial thing from a customer point of view, or if you talk about the basis of all these three different data warehouses are built on columnar architecture. When you say columnar architecture, what does it mean? Is data coming into these environments are they call as usually the ODS systems. They store the data in rows. What does it mean is if you do a select star from a SQL server, your performance is limited to that. It's going to read no matter what, whether you put a select field 1, field 2, or select star in a SQL server. The SQL server engine, distribution engine, will read the entire row of data. But whereas in a columnar format, if you say select star, the SQL, the data warehouses, what they're going to do is to read the entire row. And there's no big difference between when you say select star in a SQL server versus in a data warehouse if you're using select star. But whereas in a columnar architecture format, when you're storing the data in a columns, compressed as columns, if you say select field 1, field 2, the performance is going to be extremely different because in a data warehouse, the data is going to be read by column by column. So what you're getting into is you're reading a compressed columnar data versus reading an entire row of data. So if you're saying select, I want only 3 fields of data, you're going to read only 3 fields of data so that you can know when you filter the data based upon saying, I want to filter based upon a gender. You can always say select field 1, field 2 versus select star. You can see the performance differentiation showing what is the difference between a columnar architecture and a non-columnar architecture like ODS systems. And all three of them support all three Redshift, Azure Synapse, and Google BigQuery. All three of them supports MPP. MPP is massive parallel processing, so which means they have underlying engines that does the job for them. So we are going to look at the architectures in like less than 5 minutes. We'll see how does each of this architecture differs and how do they correlate with each other. But before we go into architectures, we need to talk about some of the important things like the differences in terms of administration and management. Since cloud pricing is elastic, pricing is elastic, and it supports, you can have a lot of surprises or you can have a lot of savings. Depends upon how you use the environment. Earlier in the olden days, before cloud came in, you need to, if you had to get a new hardware, if you're not been if you've never worked out to the cloud era, I'll tell you an experience. To get a server, to get a new data loaded into the system, we need to do capacity planning as IT administration, as IT managers. We used to do capacity planning to say, how much of capacity will I need in 6 months time? No idea. We always used to get the numbers from the air to say, oh, we need like probably like 3 terabytes of data. And so we had to procure a machine, a server, which can store 3 terabytes of data. We need 486 GB RAM for running our database. That's how we used to put it. We used to be able to tally it out, saying what we would require in 12 months or 6 months timeline. That's how organizations worked. But with cloud, what happens is everything is, since it's at the tip of your fingers, it is very easy to add more servers, reduce more servers, and depending upon where you are in terms of your architecture, where in terms of how we are storing the data, you can actually increase the scope and capacity. More data coming into the environment, most likely would be there's a more business happening in the industry, in your company organization. So from an administration and management point of view, in AWS, you have to measure exact instance size, and you have to configure your nodes. You have to list out how many nodes you need manually, and it requires you to know that AWS expertise. When I say AWS expertise is you would need at least how to know navigate everywhere. You need to exactly know what is a node means and how many nodes do I need. Whether do I need a R server? Do I need a M server? What kind of capacity I need? I need what is the kind of memory unit do I need? What kind of a VM size that I need? All of those you need to know in terms of Redshift. Whereas in Google BigQuery, it's completely orthogonal to that. It's completely serverless. Provisioning is completely automatic. You sign up for a service, you pay for what you consume. In Azure Synapse, it provides both models. It provides serverless, where you scale based upon your demand, but at the capped capacity. And you also have a dedicated option. So in serverless, what happens is if you don't use it for 1 hour, the server goes down to the base level. So your pricing is set to base at the level of what you have of a choice of the minimum base that you want to pay for. Whereas in a dedicated option, you're paying for a flat rate. Whether your consumption is high, low, doesn't matter. You'll still be paying for the dedicated option. Why you would do the dedicated option versus serverless is because I know with much more authority that there is a response time. It's a mission critical application. We need a quick response time. We cannot go with have a high latency. And you go into serverless, it takes few seconds to bring it up and bring it down, the few seconds. But whereas in a dedicated capacity, you get a planned capacity. So depending upon how you want to scale, you will set up your servers to be there. Similarly, when you look at from AWS for a scalability point of view, it's a decoupled storage and compute. So your nodes are different, your compute storage is different, you're planning it out, your capacity based upon how much of data you're bringing in. Whereas in Google BigQuery, they both scale independently of each other. It doesn't matter how you want to scale. The entire scaling is handled by BigQuery itself. Whereas in Synapse, we talk about the serverless options, it scales automatically. But for the dedicated option, we have to make sure that we add the capacity every now and then to have an eye on it so that we know what the predictability of the pricing is. The difference all comes to saying what is the predictability? Is it like, am I able to predict what is my bill going to be end of the month because I consumed so much? It's not like a Netflix where you pay $9.99 and you get a entire, sorry, it's not $16.99, and you don't say I get for $16.99 I get these many choices. It's like saying it's like more like Hulu kind of a Redshift kind of a Redbox kind of an interface where you are saying I exactly know what I'm going to purchase it. I'm going to purchase only one movie. I'm going to rent only one movie for now. So I'm going to pay $1.25. So very similar to that. So that's what it is. It means like saying, am I scalable or am I not scalable? Very system from an ecosystem point of view, all three of them have their own kind of tools. Redshift provides QuickSight for visualization analytics and business intelligence. And Google BigQuery has Looker. Looker is a fantastic UI interface for analytics. And you also have Data Studio for getting the Google Data Studio provides the kind of reporting mechanisms. Whereas in Synapse Power BI is fantastic in terms of what it can do, the capacity, not just about the functionality, but Power BI bringing in a lot of new features that are coming and it's refreshed every month. And it adds so much of value into organizations for not only from analytics space, but also from modeling purposes. Now the entire data and Power BI can hold up to 10 GB of data in its extract in its caching mechanism so that you can perform reports at the edge. Similarly, with integration and ecosystem, we saw the different architectures. So all of them provide their own native integration to multiple tools from GCP or from AWS or Synapse. They have their own integrated tools to perform your entire pipeline and plumbing work. And one thing that I'll talk about is the reason why I put out a ingestion of streaming data is from AWS Redshift. I found that it has no inbuilt Redshift streaming data integration. So they had to do it with Kinesis. Whereas with GCP and Synapse, they both can take the data from the respective NoSQL databases, and Synapse has a Cosmos DB integration too. So you can write a Cosmos DB, you can ingest the data into Synapse directly through the pipeline built over Synapse itself. So those are the big differences in terms of functionality. But that is not all. There is much more than what it can do in terms of differences. When we talk about differences, when we talk about, we have to understand how the architectures of each environment differs. So when you look at Synapse, right? Synapse SQL is for mainly it was originally it used to be called a SQL data warehouse. And we saw that the SQL data warehouse has multiple components. From Synapse, it provides you a underlying storage layer. So it's provided by ADLS Gen 2, and it also has multiple runtimes. Say Synapse has multiple runtimes with Synapse SQL, which is called as SQL pools. Whether it is dedicated or serverless, there are multiple varieties of that. And you also have Spark engines. So if you know Microsoft earlier, right? Microsoft olden days. When I say about olden days, I spent 14 years on Microsoft before moving, before I tried to do a lot of new things and different things. In the 14 years, what I've seen is Microsoft SQL. Microsoft had no Spark capability in before cloud came in. But once cloud came in, Microsoft adopted all technologies. Microsoft Azure has got amazing amount of open source technologies, and the modern, if you look at the reference architectures, it talks heavily about the modern data warehouse analytics, and it talks about the advanced analytics based upon Spark engines and based upon HD insights and based upon Databricks. Those are new concepts and they're efficiently used within Synapse itself. So now Synapse combines with SQL, Spark engines. It's seamless, integrated, and it can provide ML models with the data that is being stored with the Spark tables, and it can work along with your data lake tables that are being stored, which have a different with very limited barriers, and you can seamlessly mix and match based on your needs and expertise. And you also have the third engine called as a data explorer. It was currently it is this will complement both explore SQL and Spark engines. It can index free text and semi-structured data, mainly found in like used for telemetry purposes, log analytics purposes. So the Data Explorer provides your AI ops journeys, like for example, doing pattern recognition or anomaly detections, or it can replace your it can build analytics IoT data based upon IoT data. It can build solutions. All of them is possible with this Data Explorer. So this is the base of Synapse architecture that contains of SQL, Spark, and Data Explorer. They also provide integration through pipelines in using the data factory pipelines, what Synapse pipelines. And Synapse provides it provides its own management. It has its own monitoring and security aspect of it, and it extends the Azure security into Synapse security. It provides SQL security. It provides the Active Directory integrated security, or you can do Active Directory password security. So different security layers, you can add all of them into Synapse. And it also provides a Synapse Studio, which you can query the data or work with the data without having for a client interface. You can do everything within the cloud interface itself. So all in all, built everything in one different one top to bottom end to end layers. And all that you need to do is to say ingest the data and do the visualization layer. So apart from that, the entire thing works on Synapse Analytics. But this is amazing. But what is under the hood? How do they work under the hood? So under the hood, Synapse, I'm going to talk about mainly about the SQL architecture, because Spark is very similar architectures what we have in whether we use a Spark open source or whether we use Spark in Spark engines in Redshift, or Spark engines are not in Redshift, but Spark engines in Google Query, which we'll talk about. They're very similar in nature. So I'm going to talk about heavily on Azure. When I talk about Azure Synapse, I'm going to talk about Azure SQL. And when people talk about SQL pools in Azure Synapse, there are multiple SQLs running inside Azure SQL components. And if you look at the dedicated SQL pool or serverless SQL pool, they have in a dedicated SQL pool, you dedicate how many SQL servers behind the scenes are running. They have called something called a control node. Control node is like a manager node. It talks about saying I can generate queries, and I will tell you exactly which is the single point of entry, and I will be able to tell when I say I mean the control node talks about it. It tells you where the data is, how the data is being stored. It sends out the data movement service where it says, I want to collect all the queries, different queries, and then integrate the queries into a result. All these things are done by the control node. Whereas the compute node, which is where the MPP engines are play a big role, is in terms of diverting those queries and then making each compute node able to run those queries and generate the results back, so that the control node is able to tie up the results and send it to the user. So a lot of processing that happens within the entire environment itself, within one control node to compute node that goes around the storage layer. So there are many SQL servers running in the behind the scenes. Whereas in a serverless, the serverless is truly serverless, because the reason is, it's not because there are not many servers. There are some servers which are not visible to the users. You, as a developer, as an administrator, I don't need to say how many servers that the SQL should be able to, should be able to categorize to. I can give a maximum number and say I want this is the maximum number I can go up to, but I will be able to, the control node will be able to spin up as and many required compute nodes to do the job processing. So based upon the workload, based upon how heavy or what the schedule looks like, the control node spins up that many SQL servers behind the scenes to do the job of it. Still, if you look at it, the storage layer is all on the same. The storage is same, both in dedicated or SQL or serverless SQL, except that you have a fixed capacity. You have to increase your capacity as it demands. There's no fixed capacity. It keeps increasing as you add more data. But Synapse SQL can benefit you can benefit from independent sizing of compute power, so that you don't. It's everything is done automatically as a customer, as for you. Everything is done automatically. This is about the SQL Synapse architecture. So let's talk about Google for a change. We talk about Google architecture. Google also does the same thing, very similar to what Synapse does in terms of decoupling storage and a difference in computing. It provides a lot of flexibility in terms of keeping the cost under control, so that the expensive resources need not be running all the time. It's a different from the traditional what we talk about, the node-based processing. But this approach brings customers to bring any size of the data. It doesn't matter how big the data is, and because of the petabit network, and because of the compute and storage, it's run through something called as a Jupyter network, and they have the node which is called as a Dremel, which is a large multi-tenant cluster that executes the SQL transactions, and also based upon the cloud storage layer, which contains this 99 point many nines of durability. And I don't. All these numbers are from Google Cloud inferences. I don't watch on any of them. I do not never tested. I've never broken down any of them, so I'll not be able to say how many nines it goes up. Probably it goes up to 10 nines. I do not know. But we saw the architecture. But from under the hood, what happens is, right? So when you send a query, the query is sent to the root server. There is something called as it's not just the nodes we're talking about. The Dremel takes the entire query and it performs the execution tree. The level of the trees are called slots, and they do the heavy lifting of reading the data or doing any computation. And they also have the branches that are called mixers. These mixers perform this aggregation. It shuffles the data. It brings the entire Jupyter network, the network over here, the network layer, to move the data from an extremely, like, it's too fast. It's like rapid way of reading the data. And all these slots are run by something called as Borg. Borg is like it's a Kubernetes precursor. It relies on it sends each of the data to mixers and slots and able to read the data through this fast mechanism. And eventually the storage is called as Colossus. Colossus is nothing but Google's global storage system. It is based upon its own latest generation distributed file system, which handles replication, recovery, and distributed management, so that there's no single point of failure. And Colossus is like amazing, fast enough to allow BigQuery to perform many in-memory database, it provides an in-memory performance to the databases. Yet it provides a cheaper, parallelized, scalable infrastructure. So this is what happens in GCP under the hood. I think we are running out of time, so I'm going to go a little bit more faster now. I got a couple of more slides to finish in the next 4 minutes. And I'm going to talk about, when I talk about AWS performs Redshift exactly the same way what we saw with SQL dedicated pool. You have to dedicate capacity. You have to plan your capacity. It all runs on PostgreSQL. It has its own storage layers. You can say how much of storage layer do you need, and it provides how many compute nodes you need. So based upon the compute node, there is a leader node that provides that takes in the query, breaks the query into silos, and sends it to each of these Postgres and running in behind the scenes. And you'll be able to have the nodes combined together, combine those query results, and then send it back to the leader node. Very plain if you look at it from a very easy to explain format. But what's happening under the hood is when the leader node receives a query from the client, it does a lot of things. It parses the query. When you say parses, when you say, like, for example, select field 1, field 2, field 3 from a table, it says from a table, it breaks down into 3 things. Where is the joins? What is the filter conditions are? And what is the kind of workload required? It performs an execution planner. It breaks the query, optimizes the query into a binary tree format, and then it brings the data into a code. It generates a code internally. So the code that gets generated are automatically scheduled, saying that which node where it has to go to for getting those data. And then it provides the interconnected network of saying, hey, nodes, these are multiple nodes that are running behind the scenes. So you have as a developer, as an administrator, you have the option to choose how many nodes have to be scaled up to. And those many nodes will get this communication happening in the internally. And between these nodes, you'll be able to say dispatcher, there'll be a query processor internally for these nodes that queries the storage layer to get the data out. And then once the data from each node is collated, and then send it to the user. It also provides a caching mechanisms. Redshift also provides a caching mechanisms. These caching mechanisms provide the kind of faster recovery of data, so that if you're sending the same query once again, when there's no underlying change in the query, it brings it from the analytics database to provide a faster response time to the queries. And one more thing I want to talk about is the once the optimizer sends the queries, there is the execution engines. It's broken down into, again, like just what we saw in GCP. They will get broken down into steps, segment, and streams. Steps is nothing but a step is is a operational for a query execution. Many steps combined to allow compute nodes to perform the query, to do the joins and etc. And from a segment portion of it, the combination of several steps that happens in the middle in the data retrieval process, they get into do the compilation process, smallest compilation unit, so that they can be done by a unit of very small compute node slice. The stream is nothing but a collection of all these segments together, so that the execution engine generates the compiled code on all these 3 of step, segment, and stream. So this compiled code execute faster than the interpreted code like Python language than what we do, and we can do with less capacity. So that's how they can scale up to say, we want with lesser capacity, we want to bring the lot of results. It happens because of those execution engine that does the query plan into multiple portions of it, like steps and segments and streams. I think we are exactly on time. Let me know if you have any questions. I'll take any questions now.
Hey, AJ. So we got a question. Very good presentation, by the way. So this first one's from Nicole, and it's, how does Azure Data Factory fit into the big picture?
So Azure Data Factory, right? So Azure Data Factory, what it does, it provides pipeline management. So the data integration portion of it, Azure Data Factory, what it does is just 2 jobs. One is it provides a data movement between a full storage to another full storage. So it provides data integration or it provides data transformation. So what we call when you call data transformation, you take in a source system, you want to do your, let's say, for example, you want to make a cleanse the data or you want to transform the data from, let's say, you are going with gender stored as 1 and 0, and you want to say gender is male and female. If it is 1, it's a male, and 0 is 1 is female and 0 is male. You can take in, do the data factory, the work to do the cleansing process and the curation process to send it to the Synapse Analytics. So imagine data factory as the data movement pipeline that provides the transport. It's like a car. It provides a transport. In the inside the car, it provides you the ability to change the data.
All right, very good. Thank you very much for that answer. Then I have a new deep. Based on your experience, which data cloud would you suggest to a customer based on your experience?
See, I'm totally biased. I'll tell you that. I'm totally biased with Microsoft. I've worked with Microsoft for 14 years, but what I would say is there is no one size fits all kind of.
Right.
There is, you cannot tell a customer saying that, hey, go with Synapse or go with BigQuery or go with Redshift, because we have to think about from a environment, from a collaboration mechanisms of many things. Your security layer is one, your data, where the current data storage is second. And you want to talk about your network of components. There are many components that an organization has. So there are many things that fine tune to pick a choice of saying you have to pick AWS or Azure or GCP. It's most of the times it's driven by organizations' interest of where their data lies and their comfort. I found Azure to be more UI friendly for developers and for non-techie people to use, as I said earlier. And I found a lot of AI machine learning kind of components. It was very easy to use in GCP. And I found Redshift to be very developer focused with fixed scale, high predictable cost. So there are like goods and a lot of goods from each of them. Yep. And all three of them supports everything.
Very good. And then another question from Drawn, which service helps organize ETL? Oh, sorry. Can any of these integrate with an on-prem data warehouse? Can any of these integrate with an on-prem data warehouse?
Very interesting question. Right now, not. They don't integrate. So for providing a hybrid mechanisms, there are a lot of third-party components today that provide the kind of Uber layer, but none of them I've seen. I'm not personally from my experience. These cloud data warehouse don't interact directly with on-prem data warehousing to provide a hybrid model. So that is where you have this pipeline components to do the data movement and migration. So once you transport the data back into the cloud data warehouse, where you get the best benefit of value in terms of the resourcing. But I have not personally tried out a hybrid mechanism, and that is not something I would even recommend.
Right. And then we got a thanks from George, who had to leave at 12:30. And then a follow-up from Drawn. Can you name any on-prem options then? Can you name any on-prem, maybe third-party integrators or software service integrators?
I've personally worked with Informatica, some of the components that Informatica provides from a cloud agnostic mechanisms from an integrating point of view. So I've seen Informatica do that. There are many other companies that do that. There are third-party organizations. In fact, some of the best benefits of using third-party components is they do much more than what these three clouds do today. These three clouds do basic data transformations from one place to another place. But if you are thinking about, let's say I want to do a CDC, I want to do an incremental load and the initial load, and I want to keep migrating my cloud infrastructure, you will need to go to a third-party integrators. I found CDC is one of the biggest components of data migration. And what these three transformations, when I say three cloud transformations provided, they are limited in nature. There are like, you can do hundreds of no code, low code functionalities, data transformations. And if you look at from, again, I'm biased, Informatica CDI, the cloud data integration it provides those kind of integrations that are like, for example, you can look into the data to see whether there is a data mismatch, or whether there's a data that has to be collaborated, whether data has to be joined, or whether there are like hundreds of functions available in the market that you need to use it. And cloud providers provide the basic means necessary in terms of data transformations. They can do like A to B, B to C kind of components, but if you have to look into the data, do some kind of repeatable migrations, that is not something the cloud has been pretty good at it at the moment of time.
All right, thank you. AJ, man, this was a great presentation. We really got a lot out of it. Got a lot of different perspective. Again, I'm serious about this open cloud view for the data platform group. So if any of you know, like AJ, able to talk to BigQuery and Redshift and Synapse, bring it in. Let's take a look at different session proposals. But this was a great session. We enjoyed it very much and got some good Q&A. So thank you so much for your time. I'm going to go ahead and stop recording. It doesn't look like there's any more questions. Dron says thanks, very informative.
Thank
All right,
you
everybody.
so much, Tim.